Hello, my name is Andrew Worley. I'm here today to present a portable implementation of point-to-point partition communication. To begin with, what is partition communication? Partition communication is a communication model that's built upon previous models attempting to improve thread integration into MPI as a whole. Partition communication is based on the shared buffer communication model. The shared buffer communication model is where a buffer is shared among a certain number of threads. Each thread has a specific portion and they are responsible for that portion. Now, if in the usual model, what would happen is each thread would complete their portion, as seen here on the right, but they would have to wait for the last portion to complete before they could actually send. A better model is the one shown on the right, where each thread can immediately send their part immediately after they're done completing it. So this still has issues with overhead and a massive increase in the amount of message traffic. So partitioned communication builds upon this. Instead of just allowing each thread to send its partition when it's done, the actual sending process is offloaded to the library itself. So the library can actually decide when to send the data and how to aggregate it to limit the number of messages and to optimize the bandwidth being used. This is the Partitioned Communication API as approved by the MPI forum. As you can see, it consists of 6 functions that are grouped into 3 different categories. The first category is the initialization operations, which behave similarly to the initialization operations for persistent communication, where it sets up a persistent request object that's used to drive and check on the rest of the operation. The next section are the MPI ready functions. These functions are called by the threads to signal what partitions are ready to be sent and are used in conjunction with the MPI start function to actually begin transmission of data. MPI arrived, it allows for piecewise checking of how the data has been received by the receiver, and allows for access to the data before all the threads and data have been successfully transferred. The remaining 2 functions are proposed for MPI4 to allow for a more robust synchronization process in between the sender and receiver, as that has not been clearly defined by the standard. So what does this actually look like when you put it all together? So what it basically is, you break the buffer into partitions, the threads signal when their partition is ready to transmit, and then the library decides the underlying transmission method. And the data can be received and accessed piecewise at the receiver. So what we have created is a portable layered library that runs on top of an existing MPI 3.0 compliant platform. We've do this by using MPIX versions of the Partition Communication API and using the exposed functions from the underlying implementation. The library uses a new request object for tracking of the internal messages and the aggregation and the completion. It also includes a very basic static aggregation function, so we can actually test the effects of aggregation on a small subset of problems. The purpose of the library is for early testing and prototyping of code and allowing programmers to integrate and test the partitioned API in their code while waiting for a optimized integrated version to be coded. Our library is based around the MPIX Request object. So this is a replacement for the MPI request and acts as a full replacement for the functions in the library. So we created this object because the traditional MPI request does not have the functionality to keep track of multiple stages of completion, which is required due to how the partition communication is supposed to send and receive messages in an aggregated format. So the request acts as a wrapper around an array of MPI requests and allows us to keep track of the completion in a more fine-grained manner. Now, since we're using MPI requests underneath the hood, we actually don't have that much overhead over a traditional sending method. However, we do have some overhead. So the majority of the overhead comes from the synchronization process. So since we're using a layered library, we are not allowed to use the underlying function calls inside of MPI that are used for background synchronization in between various processes. So instead, we have to do all that inside the library itself. Now, this is difficult because it's a non-local operation, but every function inside the partitioned API is considered a local function. So we needed some way to offload the blocking functions so that the function can still return as dictated by the standard. So the solution we had is to spawn a local progress engine to actually do the synchronization process. So this spawns a single thread that runs through the synchronization process once, and then after that's set up, the thread dies and everything behaves as a single operation again. So we have a basic static aggregation setup. So what I mean by static aggregation is we have a single consistent mapping in between partition contents and the internally generated messages. So we do this by having just calculating the offset of each partition and deciding which message it will be set inside. So this is very simple and allows for easy tracking of which partitions are complete and which messages are ready to be sent, and requires only a single synchronization at the start. This does have some downsides. We do need to synchronize before we can have any progress being made, and we can't actually optimize this very well because it's very simple and very basic and doesn't have any real knobs that we can tweak on the fly. So testing the library, we had 3 different versions that we tested. The first was our layered library on top of Intel MPI and OpenMPI. The second one was actually a version of the Partitioned API that's actually integrated into the OpenMPI framework. So this required a couple modifications to the functions and a little bit of software engineering. However, this allows us to use the internal progress engine and allows us to actually test our version versus something that's integrated and actually has access to the internal update and synchronization methods of an actual implementation. So the first test we did was compare our library versus existing communication protocols. In particular, we did blocking, non-blocking, and persistent as our baselines. We tested this in both OpenMPI and Intel MPI, and as shown in both, our library performs a little bit worse than persistent communication for small message sizes, but that overlap disappears once we get past the egress limits in each of the systems. The second test we ran was comparing the integrated version of partition communication in OpenMPI with our external version running on top of it. As you can see, there's not that much difference in between the two performance-wise. The actual performance was within 0.38%, which is almost low enough to be considered just noise in the test data. Our final test was to run a modified version of MiniFE that's been modified to work with partition communication. So we ran this 3 different rounds with the different setups. The first one was we ran it with the integrated version of partition communication inside of OpenMPI. The second one, we ran it with our external library on top of OpenMPI, and then we ran a version that was just using multiple sends in parallel. So what this shows is that our solve time for all of them is remarkably similar, and there's really no variation to really take note of. However, if we look at the communication time, we notice that there is a significant increase in time for 2 threads. This is due to the setup having enough overhead that the threads really don't show any additional benefit. Also, MiniFE is not really set up to take full advantage of partition communication, as there are barriers after each calculation step. So in conclusion, what we have is a library that successfully allows partition communication to be run on top of a existing 3.0 compliant system. And while it's not optimized, our performance is not negatively affect the operations that are being performed underneath the hood. Any questions?